Hi there, in this video I'm going to briefly explain how to use an oscilloscope. I'm not going to go completely wild and go over all of the features of this machine, but I'd like just to cover how you can connect your scope up to your signal source, twiddle with these dials to get your signal viewable on the screen, and then I'm going to briefly cover how to use triggering in order to get the trace to be redrawn when a particular event happens, a voltage event.
Right, so this is the star of the show. This is our oscilloscope. It's quite an old oscilloscope, probably classified as vintage kit now. The good thing about this is you can get them cheap. I got this from the local university. They were chucking out their old kit. I think I paid 15 or 20 quid for it. For a piece of kit that would have cost thousands of pounds to begin with, this is fantastic. And it does the job, and it's great for a beginner in electronics. You can analyze loads of signals. You can use it for very sophisticated things actually. The modern oscilloscopes add a lot of essentially convenience functions, but at some point as you're analyzing higher frequency signals or more complicated signals, the limitations of this start to become a pain. But for a beginner and for intermediate, these things are fantastic. So if you can get a hold of one of these, do it. They're very, very useful. Right, just let me briefly say what's on here, just in kind of block form. On the left here, we've got the screen. So this displays on the vertical axis voltage and on the horizontal axis time. So the oscilloscope is used for measuring time-varying voltages, and it will display that on the screen. We can control the resolution of the screen with these dials. So this dial at the top controls how much time per centimetre on the screen, and there are 10 divisions from left to right there. So at the moment it's set to 0.5 milliseconds per centimetre, but we're not actually connected to anything, so all we see is a straight line. At the bottom here we can control the vertical resolution. That's how many volts per centimetre, and there are 8 divisions from top to bottom, and bottom to top. There's 2 dials at the bottom for voltage control because we have 2 probes. We can simultaneously display 2 signals. There they are. The probes are what allow you to connect up your oscilloscope to the outside world, because you need to connect it to something in order to display a signal. So let me do just that, because that'll illustrate quite clearly what's going on. So the probe here has 2 terminals on it. It's got a ground connection, and it has a voltage connection, which is what the oscilloscope is going to sample. It's important to note here that the ground connection is actually connected to ground on this oscilloscope. This becomes important because if you're measuring a non-isolated source, so, okay, let's just to keep it simple. If you, for example, were to connect this to the mains, and you connected this probe to live, then you would be shorting the live directly to ground, and you would probably burn this cable out and maybe blow up your oscilloscope. In most cases on equipment that's battery powered or has an isolation transformer or something like that, you can put the probe anywhere, but it's worth remembering that this is grounded. There's a great video on YouTube that's dedicated just to this, if you look it up, by Dave and on his EV blog. But anyway, so I have a power supply which you can see in the little inset video. And at the moment it's set to 0 volts. I'm going to connect my ground to the ground of my voltage source, and I'm going to connect the probe to the positive of the voltage source. This now is connected up, and you can see that the voltage source is set to 0 volts, so we don't see anything on the display. If I now turn the voltage up, you can see that on the display the line is moving up. And if I set it to 1 volt, or thereabouts, there we go, you can see that we've gone up approximately 1 division. This is because on our volt resolution here, we're set to 1 volt per centimetre. So 1 centimetre on the display corresponds to 1 volt, and we've just seen that that's very clear. And I can move this up and down. As it happens, I can't go more than 5 volts here, otherwise I'll go off the screen. But that's fine, because I can change the number of volts per division. So if I change it to 5 volts per division, and I go up to 5 volts, we've only gone up 1 division again. So that's what the voltage resolution is for, so that you can display large signals on the screen or small signals all on the same screen. Of course, on a modern oscilloscope, that's likely to auto range itself, but as well as offering explicit control. But on these old things, you have to explicitly set the range. Okay, now let's have a look at the time control. One thing I'll say first is that if I turn this to 0, you notice that a line's in the middle. The line doesn't have to be in the middle. There's a little dial here called the Y position, which allows us to move that, which is very useful if you have a signal with its baseline, say here, that only goes up to here, then you can see the whole signal on there, whereas if you started with your baseline there, you'd be wasting half of the screen. Right, so let's now have a look at the time resolution. I'll actually put our baseline right at the bottom. So our 0 volts is down there, and I'll go back to 1 volt per division, because that's easy to see. And the moment we're set to 0.5 milliseconds per centimetre. So we've only got 5 milliseconds from left to right. So we can't, if we change the dial on the voltage source, we're not actually going to see, all we're going to see is this line move up and down, because it's refreshing very, very quickly. Whereas if I set this to its maximum scan time, which is 5 seconds, so that's 5 seconds per centimetre, then we have a total of 50 seconds per refresh period. Now if I change the voltage, you can actually see it being drawn on the screen. And I can change the voltage to whatever, whatever we want it to be. I can mess around with it. I can create kind of semi-fake periodic signals and things like that. But this is what the time base allows you to do. So now we can actually look at long signals that have change over a long period of time and still be able to display them and see the changes. This is only possible because this is what's called a storage oscilloscope. All modern oscilloscopes are storage oscilloscopes. They have a little memory in here which stores the samples. Otherwise, we'd only be able to display it in non-storage mode. If I press this button here, this will turn storage mode off so you can see what it would look like. I can't actually have it on there. It would look like this. You would just see the trace moving around. And again, I can move the trace up and down, but we can't actually see what that signal looks like over time. If I put storage back on, then we can now see the signal. I can move it up and down, and we can see the signal. So storage allows us to store the waveform. This is very useful for these slow signals. You don't tend to need to use it for periodic signals at high frequency, because then the actual persistence of vision, the trace will be moving so fast that it will tend to look like it's kind of storing it in a way. Your brain, in a way, is being the storage for it when it gets to a high enough frequency signal. So that's what the time control does. Alright, now let's look at something a little more interesting, or a little more interesting signal, a periodic signal and a real signal. So what I have here is the output of a 24 volt AC transformer. So if I connect up these two prongs, we can now see the signal on the screen. It's too big to see on the screen, but we know what to do there. I will turn it down to 20 volts per division, and I'm going to center it using our Y position. But what's going on here? Well, we can't see it because it's a transformer that's connected to the mains. In the UK, this is 50 Hertz here, and it's refreshing too quickly. We can't actually see it, so we need to change the time resolution. So as I increase the time resolution, you can begin to see the signal. If I've set this now to 10 milliseconds per centimetre, So each centimeter is 10 milliseconds. That means the whole display is 100 milliseconds, so 1/10 of a centimeter. If we have a 50 hertz oscillation, so 50 cycles per second, within 1/10 of a second we'd expect to see 5 cycles or thereabouts. So let's see if we actually get that. And if we count the number of peak-to-peak complete waveforms, we've got 1, 2, 3, 4, and we do actually have 5 because we didn't really start at the beginning there. If we go round, we've got 5. Now, I can actually use this now to explain triggering. So the oscilloscope, in order to know what to draw on the screen, it actually has what's called auto-triggering. So it looks for changes in signal to refresh the screen. I can explicitly control when it triggers by controlling this level. So what this will do, it will wait till it sees a rise of voltage that crosses the level defined here, and then it will then refresh the screen. And so if I increase the level here, you will see that it's actually moving our signal to the left. That's because it's triggering on higher voltages. It's triggering now here. So I hope that's clear, that I can adjust when it triggers. And if I go up to the peak there, we're now refreshing at the peak. So every time it hits that voltage, it's refreshing the signal. So we're now aligned with that part of the waveform. So now we can clearly see that it's 1, 2, 3, 4, 5. There's actually 5 cycles there. So 50 hertz. So from even on an old oscilloscope like this, you can work out things like frequency. Okay, it doesn't have a nice little display that shows you it, but just using some basic calculation, you can estimate things like frequency and so on. If you need a more accurate measurement, you'd have to use a more accurate tool. Of course, you can calibrate these things, and if you're willing to go in there with a micrometer and so on, you can probably get a reasonably accurate measurement of something like frequency. What you will notice here is that this yellow light means that the signal is constantly triggering. So this is because our signal is so fast that it's 50 times per second, that it's triggering 50 times per second. Whereas on a slower signal, you would actually see the triggering happen much less often. So going back to our signal, which is from a 24 volt AC transformer, let's try and estimate let's see if it really is 24 volts AC. So we're at the moment set to 20 volts per centimetre. And if I just align this, so it's easier to count the divisions, we've actually got 4 divisions peak to peak. So that's 80 volts peak to peak. That sounds a bit suspicious for a 24 volt AC transformer. Well, because that would mean that we've got 40 volts on each oscillation of the waveform. Well, as it happens, this is correct. If you put in the calculation for what's rated on the transformer is the root mean square output. Well, approximately. They're not regulated devices. So if we put this into a calculator, so 80 volts peak to peak should correspond to around 28 volts AC, measured on a root mean square output device. So let's actually check that and see if that is true. So I'm just going to put the oscilloscope in frame here. Sorry, not the oscilloscope, the multimeter in frame here. And you can't see, but off screen, I'm just going to put this across the terminals of the power supply. And there we go, 28.8 volts AC. So besides the fact that our 24 volt AC transformer, just to show you this, 24 volt is outputting actually 28 volts. Don't worry about that. Transformers are not regulated devices. They're only regulated by their construction. So this is just typical of a transformer. It shows you why people switch to switch mode power supplies for better control over the voltage. But it also shows you that our oscilloscope is accurate in measuring voltage, and our estimated RMS matches the RMS that the multimeter reads. What I want to illustrate now is using both of the channels at once, so measuring two things at once and kind of a mock debugging scenario here. So just to explain what we've got here, there's a microcontroller over here. This is an Mbed NXB1768. So it's just another microcontroller like the Arduino. And connected to pin 20 is a resistor. This is going into the base of a 2N2222A transistor, which is then effectively switching this line of LEDs. This is external power for the LEDs. So it's not working at the moment, even though I've uploaded the program. So the first thing to do is we're going to connect a probe to the output of the resistor, or onto the output of the microcontroller. So I've connected up the probe there, and I'm going to ground it here. So it's grounded with respect to the microcontroller. So right, let's pan back now to the oscilloscope and take a look at the signal. Okay, so now I've connected up we've got a setup with the oscilloscope both. Okay, so now we've got a setup with the oscilloscope and our circuit both in shot. And let's have a look and try and work out what's going on. I've got the program running on here, but we can't see any flashing of the LED, so let's try and investigate. So the first thing I'm going to do is connect the first probe to the output of the microcontroller. Now, okay, we can see changing voltage there, so that means that the microcontroller is working. Let's see if it's what we expect. I can't really tell what the on and off period is here, so I'm just going to switch this down to 1 second per division. Now it's on 1 second per division. You can see the trace is making out, and we are on for 1 second and then off for 1 second. And that's what I expect, that's what I programmed, so I know that that's working. What about the voltage? What have we got here? Well, we've got about 1, 2, 3, 4, 5, 6 and a little bit divisions, and we've got our voltage resolution set to 0.5 volt per division, so we've got about I'd estimate just over 3 volts there actually. And that's correct because the Mbed has a logic level of 3 volts. So when it's on, it outputs 3 volts for a logic 1, and it's 0 for a logic 0. So everything's correct, but we're not seeing any flashing. So what's going on? Okay, well, let's connect up the second probe to the output circuit and see if we can see if our signal's getting through to the output circuit. Alright, well, to connect to the output part of our circuit, I'm going to use the second probe, and I'm going to connect it to the high side of our transistor, so the input of our transistor. Now we should see this be pulled down whenever the transistor is switched on. So if I press this button here, dual, we can now see both signals. Now I'm just going to adjust the primary signal. So this dial controls the primary signal. I'm just going to speed up a bit so I can easily adjust that. I'm going to move our primary signal up and out the way, so it's at the top there. And I'm going to move our second signal down. So on the oscilloscope, this primary and the secondary probes, they have their own controls. I can control both of them independently. Right, now we can see both signals on the oscilloscope probe. And something funny's going on here. I mean, look at this bottom signal. So we can kind of see that it is switching on and off, but something really weird is going on. Now, as I know what the problem is, I'm just going to alleviate you of it. But it looks very messy, doesn't it? As if there's a lot of noise on there. It's almost as if there's no voltage reference. And that's what the problem is. The secondary circuit is not grounded to our primary circuit, to our driving circuit, which means that the input to the transistor has no ground reference. Well, only the ground reference of the power supply, which might be different from the ground reference of our controller. So if I tie these two together, now we see the light blinking, and we can now see on our second probe, we see our voltage turning on and off. which is fantastic. And if I now change the voltage to, let's say, on our secondary probe, well, if we set it to 1 volt per division, just move our top probe out the way. I want that, make that a small signal. There's our top. And now I've set our bottom secondary probe to 1 volt per division, and we have 1, 2, 3, 4, approximately 4 volts, which is what I'm putting into the secondary circuit. I'm putting 4 volts from the power supply. Right, well, let's take a look at the traces now that the circuit's working. So what I want to do, I'm just going to wait till it finishes, then I'm going to press these hold buttons to store the whole trace. Okay, now we've got one trace in there stored. And so what we see is that when our circuit is, when our triggering circuit is on high, then our second probe is pulled low, which makes sense because we turn it on, and then the power, most of the power is then, voltage is then dropped over the circuit, and so we see the residual voltage there, which is low, if that makes sense. Whereas when our triggering circuit is off, so the transistor is off, then there's no voltage drop over the component, it's not drawing any power, so we actually see the high voltage there. So that's why they're kind of out of phase. But anyway, I hope that was illustrative of how you can use an oscilloscope to diagnose problems and why it's useful to have more than one probe. Because you want to be able to measure two things simultaneously, and in particular where you have a correlation between your input and output, you want to check that that correlation matches. This can be incredibly useful. And the triggering functionality, which we haven't really used, I showed you what it does. It comes into its own when you want to say you have a triggering signal that then sets off a series of events, maybe some kind of transmission over a transmission line, and you want to, there's something wrong with it, and you want to debug a particular aspect of a signal, and so you'll use the triggering functionality to trigger a capturing of the scope read of the voltage readout on the scope, and then you'll be able to analyze your signal and understand what's going on. Final thing I want to say is don't be intimidated by modern equipment. So we've got a Rigol DS1074Z. This is a kind of entry-level, decent quality oscilloscope, modern oscilloscope. It's got 4 probes, but otherwise it's pretty much the same. Yeah, there's some more sophisticated stuff in there, but it does effectively the same job. I've connected the probe of channel 1 up to the output of the microcontroller, and you can see that it's going as we expect. And if you look at the controls on here, you'll basically see the same thing. So I can adjust here the scale, which is the temporal resolution. And I can adjust the horizontal resolution, and position, things like that, so that I can then see the trace as I can see it on here. So once you're familiar with this, which just gives you the basics, you'll find you'll have no problem with using one of these more sophisticated ones. So I want to give you a couple of tips in case you do go away and you want to buy one of these old oscilloscopes. The most important thing you should look for is make sure it is a storage scope, because you want to be able to store the waveforms, so you can look at very slow waveforms and that you can store triggered waveforms and so on. So make sure it's a storage scope, and when you look at old oscilloscopes you will find that there are non-storage scopes out there for sale. So, and you could easily overlook that, I guess, if you're a beginner and you've just seen this video. So make sure it's a storage scope. The next most important thing you want to look at is the bandwidth of the oscilloscope. The higher the bandwidth, the better. The bigger the bandwidth, the more accurately the oscilloscope can sample and represent your signal. So if you've got sharp transitions in there and so on, the more accurately those will be represented. So the higher the bandwidth, the better. Apart from that, if you get more probes, that's good. You can measure more signals simultaneously. If you've got a kind of little display on here that maybe shows you frequency and so on, that can help. You analyze the signal. But otherwise, just make sure it's a storage scope and go for the highest bandwidth you can find. Alright, well, I hope that was useful as an introduction to the oscilloscope. You now know how to connect up your probes to view a signal on there and how to adjust the dial so that you can understand what the signal means. Hopefully you also understand not to be intimidated by equipment like this. It's pretty simple to use. Now if you look at it, and we've also seen that with a modern oscilloscope, whilst it's a lot more looks a lot more complicated, in essence it's doing the very same thing. So you shouldn't be intimidated by a piece of a modern oscilloscope either. And I'll just say again, even these old oscilloscopes are incredibly useful. It's probably one of the most useful things you can have as an electronic hobbyist. So find yourself an old oscilloscope from a local uni or eBay or something like that. Alright, well I hope that was useful to you and thank you for watching.